Yes, there was a question. The question was that supposing we see a bifurcation diagram something like this, we have a periodic orbit coming, a period doubling occurring, and finally at this point, without going through further period doublings, supposing it gets into a chaotic orbit like this. That was the question. Yes. How can that happen? Obviously, if you have such an event, there is a sudden expansion of the attractor, and that sudden expansion of the attractor can only be caused by I already done that, by interior crisis. Okay. In order for there to be an interior crisis, there has to be unstable fixed points, saddle fixed points, their stable manifolds, and then this orbit touching the stable manifold. That is the kind of phenomenon that I talked about. So, his question is, where is that unstable fixed point, whose stable manifold we are talking about? Obviously, at this point there is one unstable fixed point here, but it is not this one that you are talking about, because it has gone beyond this range. So, there is something more that must have happened in this part. Well, whenever you see this, the immediate conclusion must be that there must be something happening here that created those saddle fixed points whose unstable manifold were involved in this event, which means that there must have been some kind of a saddle node bifurcation leading to the creation of another orbit, say period 3, and that went through a succession of period doublings to some extent, and then finally at a boundary crisis this fellow went out of existence, not out of existence, out of stability. So, this fellow became unstable, but still it continued as the unstable lines, and these are the ones that have been involved.
So, from the beginning it is unstable?
No, some part it was stable, it existed as a coexisting attractor, and then through a boundary crisis it became unstable. When it becomes unstable, still it exists, and that is what ultimately manifests itself when it touches the actual stable periodic orbit, as a result of which the whole thing becomes then stable, which in this case is a chaotic orbit. Okay. So, that is a mechanism by which you can see a sudden expansion of an attractor. Well, today we will do something else. We said that a chaotic orbit is one in which a large part of the state space is covered. That means, if it is a one dimensional system, the state space is one dimensional, and the chaotic orbit will not be confined to points, it will be covering a set, say from here to here. Okay. So, when that happens, that means you are covering a set. It is distinctly different from the periodic orbit in the sense that when it is periodic orbit, all the points fall on some specific locations, while if it is chaotic orbit, it is distributed. In that case, obviously there is no reason to believe that within this range the density of orbits will be the same, it might be different. So, one of the ways of characterizing a chaotic orbit is to find out how are the points distributed. Okay. Means some part will be might be distributed, some part might be densely populated, some parts might be sparsely populated. So, that talks about the character of that chaotic orbit, especially if that state variable represents something, for example, a voltage or a current, then depending on whether the higher part is more populated or the lower part is more populated, you will get a higher voltage or higher current, or lower voltage or lower current, right. That is why it is necessary to have some idea about the distribution of the points. Now, how do you find out the distribution of the points or the density of the points? If say you have the normal logistic map distributed between 0 and 1, then the way to find out the density of points falling in different parts is to divide this state space, in this case one dimensional state space, into bins. Say this is a bin, this is another bin, this is another bin, and so on and so forth. And then as we iterate the map, wherever the iterates fall, on that particular place a particular bin's content will be incremented by 1. Okay. So, if you go on doing that, what will happen? The bins will keep on filling up, and there will be some bins which will be more populated, that means there will be large number of points falling on that. There will be some which will be sparsely populated, less number of points will fall on that, and then we can count, right. And you can easily figure out that this can easily be done in a computer. That means this state space can be divided into such boxes, and you can count the number of iterates falling in each box. Okay. And then we will define the density function as rho of x So, obviously, in order to get something reasonably approximating the actual density of each box, you will have to take a large number of such iterates, for example, a million of them, right. If you take a million, that means in the denominator it will be a million, and in the numerator for each box there will be a certain number. If you divide, you get the density. Clear? Can you do this exercise for the, say, the logistic map? Simple enough to write on a computer program. You
have to start with different initial conditions. And
yes, here there is a question, which initial condition do we start from? Obviously, if you start exactly at a unstable periodic orbit, say here there is unstable periodic orbit at this point, if you start exactly at this point, where will it be? That million will remain there. Okay. So, that is a very atypical initial condition, but since it is unstable, any slight deviation from there will make it go into the chaotic orbit. So, there are a finite number of very atypical points from which you will not start, but obviously in any computer program it will be impossible for you to start from there because of the round of errors. So, when you are actually writing the program, it does not really matter, but mathematically it does, and therefore, you will say mathematically that starting from any typical initial condition. This typical is not the English typical, it is a mathematical typical, means these are not the atypical special points. Just choose arbitrary any point, and you land up in a very typical point. Yes, that is a definitely important point there. Now, you might ask, what use is this function? Ultimately, you have landed, suppose in this case, you will, if you do this exercise, you will find that you are landing into a function like this. With the logistic map, it will be a function like this. So, here is the rho of x and here is x, that is the density, which means that the density is higher to the two sides near 0 and near 1, and in between it is low. If you actually do this exercise, you will find it. In other systems, it might be something like this, say, possible. That means there is some kind of a function that has a larger density towards the higher side. So, even though it is chaotic, you will easily notice that the average value of that is very well determined by the density. Clear? Here the average value would be, since it is symmetrical for this part, the average value would be something like 0.5 in this case. Here it will not be. So, obviously, it would be to our interest to to find out this invariant density. I have said how to do that numerically. Simply iterate that, count the number of things come in a box, and you can do that. And you can also visualize that this can be also done in 2D. For example, if you have a 2D space, if you have a 2D space, and here if you plot the row, then the density function will take the form of a surface, some kind of a surface you will get, and that surface will say for this a particular value of x y, what is the probability of finding the state there, right. So, it is also related to the probability, the densities are also related to the probability, and it will be a nice exercise to do this for example, the Henon map, where you know that the system goes to chaos beyond a certain parameter range, and to find out by this counting of the boxes how many fall in each bin, you will find the density. But you might also ask, can we do that analytically? For some systems at least, can we do that analytically? Can we obtain, can we derive the density function? There is a very interesting theory for that, and that is what will be the matter of discussion today. Yes, it is possible to do that in some classes of systems, but before that let us try to understand something, a very interesting and important concept. Suppose you have a map something like this, say x here, f x there, and the map is like this, say, and I am talking about okay, let us start from some other point, then I will come there. The point is that I have said how to do this, that you start from an initial condition and go on iterating it, it will fill up the bins, and then you ultimately get there. We might also approach the problem from a different logic. You might say that suppose there are a very large number of initial conditions situated on this line 0 to 1. Take a large number of initial conditions and apply to the map to all of them. Okay. Suppose you have started from a uniform density, that means there is a equal number of points in each bin, and that is where you started. If we apply the map, they will be differently distributed again, there will be a different density function, right. As a result, what we are doing is we say start from a uniform density and then uniform density like so. It might not start from uniform density, but for the sake of logic I said let us start from uniform density, but as a result the application of this function on each point, it will then be differently distributed. Again, if you apply the same map on each point, again the density will change, right. So, suppose it gets this density, so on and so forth. You can go on applying this logic further and further. Ultimately, it will converge onto some kind of a density function, right. Ultimately, it will converge onto some kind of a density function, subject to certain conditions, of course, provided the iterates do not go to infinity and stuff like that, provided the attractor is confined to certain ranges and things like that. These are common sense conditions, so I am not going into the mathematical details of them. Point is that it is logically anticipated that this procedure will ultimately converge onto some kind of a density function, right. That density function, say it has converged onto say this density function. This density function will have the property that if you apply the map once again on this density function, you will get the same density function. Okay. This is called the invariant density. This is called the invariant density.
So, 2 days density function is same.
What?
I mean the first density function.
Yes, yes, that's my point. Next, I have then defined two types of density functions. One, I started from one initial condition and have gone on iterating the map. That means I have generated a time sequence, and then we have found the density of that. In this case, it is an ensemble of initial conditions whose densities have evolved and finally homed onto some kind of invariant density. And so, here it is the ensemble average that I am talking about, and in that case it was the time average that I was talking about. Now, there exists a theorem proved by the famous mathematician Birkhoff, I will come to the specific mathematical terms, ergodic and stuff like that later. But presently, what Birkhoff essentially says is that for ergodic systems, these two are the same. That means the time average is equal to the ensemble average. The mathematical terms I will come to a little later. Essentially, you might say that a ergodic system is where a large part of the state space is covered, so that if you start from any initial condition, it will visit the neighborhood of any other part in finite time. Is that point clear? Suppose it's a chaotic system like the logistic map. Like the logistic map, suppose you have got a bin here, and you have started somewhere. Then you will be able to say that within some finite number of iterates, there will be at least one iterate falling within this bin. That means every part of this range is visited. So, such systems are called ergodic. But rigorous mathematical definitions are not all that necessary for you. The point is that for ergodic systems, chaotic systems are ergodic systems, then the time average is equal to the ensemble average. So, instead of starting from an initial condition and waiting for a long time so that you can measure the time average, you can do it very fast by working with the ensemble average, right. Because as I said, in order to get any proper density with the time averaging, it has to take a long time, millions of iterates, then only you get a more or less accurate description of the density function. But with the ensemble average, you can do it much faster. That is why we often prefer to do it by ensemble average. Essentially what we do, we know the function, we know the map, we start from any arbitrary density and then go on iterating it, and then finally within some iterates we will see that the function, the density function has converged. When it is converged, we say that it is the invariant density. Now notice that something is happening here. Here we have some function over the range 0 to 1. In the next iterate, what we have? Another function over the range 0 to 1. Next iterate, what we have? Another function over the range 0 to 1. So, as we are working with the ensembles and applying the map to it, what is happening? A function is mapping to a function, right? And then we will be able to define a function that operating on a function gives this function. Is that concept clear, or should I repeat? Obviously, here we can say that an operator is operating on this function to give me this function. At the base of the operator, we have this map, in this case maybe the logistic map or whatever. But ultimately that map is defining an operator which, when applied on a density function will give me a next density function, again it will give me a next density function, and so on and so forth. Ultimately, what is the invariant density? The invariant density, when you operate on it by that operator, will give me the same invariant density. What does it mean? It is a fixed point. It is a fixed point of that operator. The invariant density is the fixed point of that operator. Okay. So let me write down what we say. This function, this operator is called the Frobenius-Perron operator. Okay. So what is a Frobenius-Perron operator? Say, suppose it is defined by the function p, which when operated on rho of x in the nth iterate, this is the density in the nth iterate. If you operate this operator p on it, it will give me rho n plus 1 of x. Okay. And the invariant density is the fixed point of this operator p. You might ask, okay, conceptually it is fine that there is a operator. Can we really write it down, this operator? Of course, that is a valid question, and let us try to address this issue. And that is exactly why I drew that. Let me get back there. Yeah. Suppose you have the function like this, and suppose you are starting from this range where we have some kind of a rho defined. And I am trying to find out what will be the rho, what will be the density in the next iterate in that range. So you notice that this goes to so whatever was the density in this part, in the next iterate that will be redistributed in this range. Obviously, if there are say 1000 points in this range, those 1000 points will be distributed in this range, and if this range is larger, it will have a lesser density, right? How less? It is not difficult to see that it is less by the slope, right? If the slope is unity, it remains the same density. If the slope is greater than 1, it becomes less. It is less than 1, it becomes more. So it is this density divided by the slope. Okay. So the Frobenius-Perron operator is nothing but the Frobenius-Perron operator is taking me from here to here, and therefore the density here is nothing but the density here divided by the slope here, slope at this point. How will you write it? If this is here, the density is a rho of x at the nth iterate, then rho at the nth iterate here is this divided by calculated at, suppose this is x1 at x1. Right. Well, now this is not the whole story. Why? Because suppose the map is like this, then the density in this part comes not only from here, but also from here, because this part also maps to the same part, right. So here it goes to this range, from here also it goes to this range. Since it does so, ultimately when you have to write it, you will have to write it as a summation. Okay. So, ultimately when you write it, it has to be written as a summation, and let me write on a separate piece of paper. So, rho of n plus 1 in the range y and y plus delta y is equal to rho n. Suppose this y comes from x1, x2, x3 and all that. So, you will have to write x1 plus x1 comma x1 plus delta x1, x1 plus x1 plus x1, and this is x1 plus delta x1 divided by dy dx calculated at x1 plus density in the nth iterate in the range x2 and x2 plus delta x2 divided by plus so on and so forth. Okay. So, this is the Frobenius-Perron operator. This is the Frobenius-Perron operator. In fact, you can obtain the invariant density for the logistic map, as I told you, both by iterating from the same place, starting from one condition and going on iterating, also by this. How will you find the Frobenius-Perron operator for the logistic map? Let us try to work it out. Logistic map, it was like this. Here is x, here is fx. Suppose we divide it into 100 bins. For this bin, here is the slope. For this bin, here is the slope. For this bin, here is the slope. So, all you need to do is to say that here, suppose in the first iterate, if I have some kind of a density rho over this, that means here there is a rho, here there is a rho, here there is a rho, and so on and so forth, then this rho will have to be divided by the slope here plus, say, notice that here there is, it is 0 to 1, here there is, it is 0 to 1. Then if this is divided into 10, 100 parts, 100 bins, this is also divided into 100 bins. Now, this bin, you will have to ask yourself, where does the iterate come from? It can come from either here or here, right. So, when you write down the Frobenius-Perron operator for this particular bin, you will say that here the density is whatever the density was here and here divided by the slope here and the slope there. Similarly here, similarly here, similarly here, and go on to cover the whole thing. Now, once you have written down or codified in a program this Frobenius-Perron operator, all you have to do is to start from any initial condition and watch as the density evolves under the application of the Frobenius-Perron operator. It will also converge onto the same density function. Take this as an assignment. This writing again is a very easy thing to do. You cannot really understand or appreciate nonlinear dynamics without actually doing it yourself. Yes.
Sir, won't there be any problem if the curve is not symmetric?
No, there won't be any problem with the symmetry. For example, if the his question is, if the curve is not symmetric, will there be a problem? Say the curve is like this. Okay, it is a non-symmetric curve.
So then how will we calculate this density?
Yes, let me tell you that. So, suppose this is normalized to 0 and 1, and here is the same thing maybe. What will happen if it is does not reach to 0 and 1? If this is not 1, what will happen? Nothing will reach that range. Suppose this is 0.8, there will be no iterate falling in the range 0 to 0.8 to 1, and therefore, that part will be empty, will become empty. Okay. Suppose you start from a point between 0.8 and 1, it will come to a smaller range, and ultimately that part will become empty. So, assume that there is some range. So, in that case, what will you do is, from here you again divide this range into bins. For this particular bin, and in this side there will be similar bins. For this bin, where does it come from? It comes from either here or here, it comes that way. So, you have to add up the two slopes here and here. Okay. That means, whatever was the density here divided by its slope plus whatever was the density here divided by its slope. Then go to the next one, whatever was the density here divided by its slope plus whatever was the density here divided by its slope, so on and so forth. Okay. So, it is still possible, it is not difficult to do it if it is non symmetrical or anything else. But there are a finite class of problems systems where it can be obtained in closed form, and they do represent a reasonably available class of practical system. That is why this will be of interest. So, can it be, can the invariant density be derived? Let us address that problem. Of course, it cannot be derived in closed form for just any given system, no, it has to be numerically done. But as I told you, there are two types of numerical procedures, both leading to the same result. The most convenient would be to start from a function to slowly apply the Frobenius-Perron operator to converge onto the invariant density. The class of problems in which this can be obtained in closed form, do you understand what a closed form is? Where you can write down, where you can write down the functional form, are those which are piecewise linear. That means, say something like this, a function x to f x and the function is piecewise linear. Not only that, you notice that here is a breakpoint, here is a breakpoint, here is a breakpoint. The maps in which breakpoints map to breakpoints, they go by a special name, that is the Markov map. Let us try to understand what do you mean by breakpoints mapping to breakpoints. Let us consider this map. So, it is something like this, the way I have drawn actually. So, this is x n plus 1/3. So, this is 1/3 plus x n. So, the slope is unity, it reaches this point, and then what is this part? When x n is equal to 1, it reaches 0. So, it reaches 0. Now, you see what do I mean by breakpoints mapping to breakpoints. you might say that this is a breakpoint. Where does it map to? 1 maps to 0. 1, if you substitute 1 here, because it is in this range, 1 here, you get 0. So, 0 is a breakpoint. So, it satisfies that condition. 0 maps to 1/3. 1/3 is a breakpoint. So, you can say that there is a situation where breakpoints map to breakpoints. Okay. Now, let us try to tackle this problem. In order to tackle this problem properly, actually I need to draw it correctly, because this should be 2/3 and this should be 1/3. So, let me draw it correctly, then it will be easier for you to appreciate what I am talking about. So, see, starts from 1/3, goes to this point, and then it falls like this. That is the shape of the map. This is 0, 1/3, 2/3, 1, 1/3. Will this system harbor a ergodic behavior? That means a chaotic behavior. What is your anticipation in this map? Do you anticipate a chaotic behavior? Why? No, it's not. It's not because of that. See, if you start from here, what is the essential thing for there being chaotic orbit? That there has to be exponential divergence of nearby orbits. Expansion. There has to be expansion. In a chaotic, in a logistic map, there was expansion. Here also, you see, if you start from two very nearby initial conditions, here is a slope 1, and therefore it does not expand. But anything falls here, it expands, because the slope is greater than 1. Now, any iterate can fall either here or there, right? If it falls here, the slope is unity. If it falls here, the slope is greater than 1. So, any periodic orbit will be having, say, a period 2 orbit. If I ask you what will be the eigenvalue, what will be the slope of this second iterate, it will have either both points here. It cannot have. It cannot have a period 2 orbit with both points here. Why? Because if it falls here, it will go that way. It cannot fall in the same part. It has to be one part and another part here. If the slope here is 1 and the slope here is greater than 1, what will be the slope of the period 2 orbit? Obviously greater than 1, because the two slopes will be multiplied. What will be the slope of a period 3 orbit? Again greater than 1, because it could be either here or there. Their slopes will always be greater than 1 when multiplied. So, obviously, any periodic orbit will be unstable. Yet, if you have a bounded orbit, it must be chaotic, and that is why this orbit is actually chaotic. So, here is a chaotic orbit, a system that is ergodic, and therefore, we can apply the Birkhoff's ergodic theorem, and therefore, if we start from any density function, we can apply the Frobenius-Perron operator to arrive at the invariant density. So, let us write down the Frobenius-Perron operator. There are 3 chunks, say A, B, C. Here also A, B, C. Okay. So, let us first consider rho in the chunk A in the n plus 1th iterate will be where will it come from? It will only come from this part. Okay, whatever is there, only if any iterate is in the last part C, it will go to A. If any iterate is in A or B, it will not go to A. So where does it come from? It comes from rho n of C divided by the slope here, and the slope here is how much? 3. The slope here is okay minus 3, but you essentially what okay, then in that case I will write it correctly. I have to write it correctly. It is actually the magnitude, because we are talking about how much does it stretch. We are not talking about the sign. Sign carries no sense here. So 3 by 3. Clear? Next we come to rho of the chunk B in the n plus 1th iterate. Where does it come from? It comes from A. So anything A goes to B, and also anything in C goes to B. So rho n of A, what it was, divided by its slope is 1, plus it now comes from two different places, rho n C by 3. All right. Similarly, rho of C in the n plus 1th iterate is equal to, where does it come from? B and C. So rho n of B divided by 1, because the slope here is 1, plus rho n of C divided by 3.
So what essentially you are doing, if you sum all these up, it will be more than 1, because you are adding rho n C by 3 twice.
No, it will not be. It will not be more than 1. Wait a minute. It has to be normalized at a later stage. But I'm not going to add them up directly, because if you do so, it is simply going to add it up. That's not what I'm doing. What I'll do next is argue that here we have the next iterate of the Frobenius-Perron operator. Okay, there was a density function here. Applied on it, the Frobenius-Perron operator gave me this, and we can now write it in matrix form as rho n plus 1 of A, rho n plus 1 of B, rho n plus 1 of C. This matrix, this vector, is equal to some matrix. This matrix is 0, 0, 1/3. 1, 0, 1/3, 0, 1, 1/3, right, times rho n A, rho n of B, rho n of C. See what I am doing? I am saying that if, say, we start from any arbitrary densities in the chunks A, B and C, here we are taking boxes. Here is a box, here is a box, here is a box, and we are not considering that the density within the box is different. We are considering that situation where we are assuming that the density within the boxes are the same. So if these are the densities in some iterate, then it will be multiplied by this matrix to give me the density in the next iterate. So this is my Frobenius-Perron operator finally. Clear?
It's not going more than 1. If you just add also, it also is not going more than 1.
Wait. There is a normalization that we have to do. Wait. I'll come to that. There is a normalization issue here. Now notice that ultimately where are we going? Ultimately we are interested in finding the invariant density without really doing the exercise of iterating and iterating. Invariant density means in the left side and in the right side it should be the same thing. So ultimately we are talking about a situation where we are talking about rho star A, rho star B, rho star C, these are the invariant things, is equal to this matrix times rho star A, rho star B, and rho star C, and this is this matrix here. So this is 0 0 1/3, 1 0 1/3, 0 1 1/3. Do you notice what is happening here? Very interesting. It means that we are interested in finding this. This is nothing but the eigenvector of this matrix with eigenvalue 1, right? This is nothing but the eigenvector of this matrix with the eigenvalue 1, because this matrix, this vector when operated on by this matrix gives me this vector. So if the eigenvalue is 1, then you are getting exactly that. So what is the eigenvector? So it is essentially eigenvector problem. Can you find out this eigenvector with eigenvalue 1? You already have learned how to find it. In a 3D map you can find it. Huh? No. Write down the eigenvector equations. Write down the eigenvector equations. See, eigenvector equations are indeterminate. The point is, you have learned that earlier, right? The eigenvector equations are indeterminate. You will not be able to find it. There will be two equations leading to the same things, same equations. So you cannot really find the eigenvectors like 1, 2, 3. You cannot find it. No, wait. Yes, that is where the normalization comes. The summation has to be 1, because we are talking about densities. No. Here there is a little bit different ball game. Though we are talking about the eigenvectors will be indeterminate. Logically, eigenvectors are certain directions. That's all. Any vector along that direction will be an eigenvector. But here we are looking for a specific eigenvector with the property that the total has to be 1. Therefore, in addition to this, we have to, so we can write down the equations as rho star C is thrice rho star of A and rho star of B is equal to twice rho star of A, but that is where we end. What you did was you assumed this is 1 and then 2 3. वो नहीं होगा. That cannot be done. So in addition to that, we have to write that 1/3 rho star A plus C, this is equal to 1. Okay. Once you solve this, in addition to this, you get the numbers. So what do you get? No, not 1/6. Find correctly. What do you get? 3 equations, 3 unknowns, you can solve it. Don't tell me that you cannot. You get rho star A is half rho star B is equal to 1 and rho star C is equal to, yes, which means that even though I have not done any iteration, I can immediately write down. I can write down the function, the density function as 0, 1/3, 2/3, 1. It will be half 1, it will be a step, it will be another step. Sorry, I wrote it wrongly. Which means there will be a large, even if you do not do all this, you start from this map and start from any initial condition, go on iterating it, then there will be a larger number of points falling in this part, a smaller number of points falling in this part, and a smaller number of points falling in this part.
What do you mean by density greater than one?
What? Density?
Rho star A greater than, say, rho star B greater than one.
No, no, no. Here the issue is that their collection put together. Here is the normalization. Their collection put together has to average to 1.
But from the definition of rho A, summation of rho should be 1.
Integration of rho over the period should be 1. So 1.
Yeah, integration of the row over the range 0 to 1 should be 1.
So sir, then the definition was
Wait, let me see where I wrote the definition. Oh, sorry. Has to be integral from over the range of x,
Over the box range.
whatever it is, huh?
Over the box range.
What?
Over the box range.
Yeah, over the box range. Sorry, this is the right definition. I'm sorry. Basically, it has to be integrated over the range of the boxes. Then that is the right definition. Okay. Clear? Okay, we'll end here and we'll continue in the next class. So remember that it is an assignment to write the program for this. I mean, writing the map is trivial. See, you might do it for the logistic map, you might do it for this map, or you might take, instead of 3, you might take 4. Everything will be the same. Huh?
So may I ask you a question?
Yeah.
Sir, say there are 3 ranges
Yes.
in which the C is mapped to A, B, and C.
Right.
And that is from 6 by 9 to 7 by 9, 7 by 9 to 8 by 9, and 8 by 9 to 9 by 9. That's 1. Now you take, say there are 300 points. Now so 100 points in each range maps to the individual A, B, C range. Now say 100 points map to one range, and it is the actual length is increased because of the slope.
Yes.
So it is actually, isn't it? I mean, you have written rho C by 3. Isn't it rho C by 9 if you take that one? I mean,
No, not really.
So we are taking uniform density here.
Yes, that is because of the Markov map property, that in the Markov map you can, since breakpoints map to breakpoints, you can divide the range into some finite range of such boxes, large chunks. It's not small 1 by 100 kind of chunks, large chunks, so that boxes map to boxes. Okay. That means it's not that some box, a part of it comes from here, another part of it comes from there. It should not be like that. You can easily and clearly define that this box comes from this box and that box. So that is the property of the Markov map. What is the Markov map property? I said the breakpoint should map to breakpoints, and that gives in the advantage that boxes map to boxes, and that is exactly why we could say that this box, if it has a particular density, then in the next iteration it will be redistributed, but ultimately your point is if we can divide into different densities in this part, right? That's where your question came from. Yes. Yeah, that would be necessary if, would have been necessary if you could say that no, the whole of A does not come from B and C or something. Rather, the whole of A, in order to define it, a part of A comes from here, another part comes from there.
I have a point. So from 8 by 9 to 1 by 9, so there are 100 points.
No, wait. Let me clarify it, then you come there. ultimately the density in the boxes has come from somewhere. Has come from where? In the previous iterate it came from, so it came from B and this part of C. Okay. If C happens to be uniform, if C happens to be uniform, here it will remain uniform. If you start from uniform, it will remain uniform. In the next iterate also it will be uniform. In the next iterate, that means that ultimately the density over C will be uniform. If it is uniform, see, even if you start from different densities within these 3 chunks, they will ultimately even out. Why? Because C is coming from B and only one part of this which is uniform. So, even if you start from, you try that at home simply by writing a code, so that you start from a different initial condition, different densities, you will find that mysteriously they are all evening out. Why? Because of this property of Markov map property. What is the point? Okay, let us stop now and we will continue in the next class.